All right. We were talking about the scheduling of final exam. Well, I have to ask other professors like how the school will determine our scheduling our final, or it's just up to instructors. But anyway, I will try to get you guys posted about our final exam schedule on the date and time so that you can like make arrangement accordingly. And also for our final exam, it will be just like what we did for the midterm. So it will be online. If you can like go home early, I mean, like your other classes will not delay your trip, but you can like take our exam anywhere you want because it's just an online exam for a final. Well, that's I guess that's the pretty early announcement. But anyway, I will get you guys posted about the scheduling or final because right now I have no idea like which exact date it will be. But we'll get you guys posted once I get it. Okay, let's get back to the material for this week. Hopefully you can see this. And for this week, we will talk about linear regression. So, well, I put this chapter right here. By the way, this is a chapter 12 from our textbook. I put this chapter here because the main purpose is to show you what you learned previously. Okay. Good evening. Yeah. Well, let me close this chat box. So what we have previously learned, like the confidence interval, hypothesis testing, it all can be applied in this chapter, linear regression. And linear regression is a very important topic in statistics. Like if you go to industry, you know, like many of the projects would use linear regression or regression in general. But anyway, the purpose is to tell you what you learned in previous chapter is really useful. Let's get to the material. So first of all, it's a definition about what is regression. If you have never heard about it, but it's rare, right? I bet many of you have heard of this regression term. Well, let's define it anyway. So from a book, this is a very popular textbook, like for linear regression class. So from this textbook, I defined it as the regression analysis is part of statistics that investigates the relationship between two or more variables related in a non-deterministic fashion. So basically, the keywords is to investigate the relationship between variables, non-deterministic fashion, or you can think it as there is some randomness involved. And I got another definition from this Harvard Business Review, saying regression analysis is a way of mathematically sorting out which of those variables does indeed have an impact. And it answers the question like, which factors matters the most, which can we ignore, and how do those factors interact with each other? And perhaps most importantly, how certain are we about this, all these factors? I think this is a more comprehensive definition for regression. You can perhaps get some idea, like we try to figure out like which variable matters the most important, and their interaction and how certain we are about them. Well, that would relate it to like our estimation and some test we can do for those estimates in the regression. Well, there is another definition saying that regression is a functional relationship between two or more correlated variables that is often empirically determined from data. So we have data and we will build up the relationship between those variables. And it's used especially to predict values of one variable when given values of the others. So this definition kind of emphasizes on prediction side of the regression. Like once we get our estimate, like how do we do prediction? So all this like emphasize some aspect of regression. Yeah, so this is, I feel like give you a couple of the definitions that you might get a better idea about what it is. Okay, let's see what, let's see how can I get rid of this. Anyway, never mind. Let's just look at this page. What we talked about, we are building relationship between variables. Like there are some relationship between variable. Let's focus on the simplest, where we have only two variables, y and x, and we use, so their relationship would be a straight line. That is simple linear regression. Simple, that is referred to, we have only two variables, y and x. And linear regression, linear, you know, it's a straight line. So that's why it's called linear regression. So we model y as a linear function of x. So we normally, our first step would always be plot your data. You will put your y variable, where I name it as response because like, yes?
How are you?
Oh, so I'm fine.
Well, is that someone asking a question? Or is the background noise? Well, I didn't follow. Anyway, we're saying this, we're modeling y as a function of, okay, all right, yeah, it's some background noise. Well, so we will model y as a linear function of x, and we plot y on the y-axis, and we plot x on the x-axis. And like there are some terms for this y and x. So y is the response variable, so I call it response here, and x is the predictor. It's called predictor. So I put predictor here. And we will always plot the data first, make a scatter plot like this. And well, in terms of data, so when we look at our, either it's a CSV file, like a spreadsheet, or we have like just data table, just like in our homework, you will see, well, the homework will get to you midnight of today. So when you see the homework questions, you will see it give you the data where they are in pairs. You have x1, y1, meaning like the first data point, x2, y2, the second data points. But anyway, they are in pairs, and we are plotting each of them, like x1 and y1. Maybe they are here, like the x1 value, and the y1, the value of y1 corresponding like this. And yeah, x1 is the first value of the x variable vector, and y1 is the first value of the y variable vector. So basically, well, in R, maybe I'll show you right now, like in R, you will have like two vectors. this will be an example we'll focus on later, but this is the data, what the data looks like in R. Like you have a vector of X variable and a vector of Y variable. And this basically this is your X1 and this is your Y1. So they are in pairs and the lengths of X and Y would be the same, right? So X1, Y1, X2, Y2, etc. to Xn, Yn. So this is what your data looks like. They are in pairs, and yeah. Next is the terminology in regression. So X, I said, it's called predictor, and it's also called explanatory variable. And Y is called the response, or you can call it a dependent variable, because like Y is kind of depend on X. So we said here we model Y as a linear function of X. So Y kind of depend on X. So Y is dependent variable and X is the explanatory variable or predictor variable. So no, I'd like to just put everything here. So what does that mean in practice? So X is thought of as a possible predictor for Y. So we use the variable X to predict Y. In experiments, X is set by the experimenter. So like we could have a couple of factors to set up and we will see how the response will be like in the experiment. So Y is a response that we observed. And in observation study, both X and Y, they are observed, but it's thought that the outcome of Y would depend on the outcome of X. So we're assuming that Y would depend on X. So if we have observed both X and Y, and we're thinking Y should depend on X, so we will build a linear regression line for them. So for example, in this case, if X is the number of hours you train, like practice running, like Y is how long you take in the race. Or in this case, it's highly likely that the value of Y, the time you spend in the race would depend on how long you practice, how many hours you have been trained. So this is like the relationship of Y and X and what they are, and we will see. Yeah. Let's make sure that we know the data, how the data is laid out. Like we have random variable Y observed at n independent realizations. Like I mentioned, we have Y1, Y2 up to Yn. And the random variable X observed correspondingly, we have X1, X2 up to Xn, and they are correspondingly 1 to 1. And for the fourth participant in the race, X4 is their time training and Y4 is their finishing time. This is to make sure that you know what are these, like Xi and Yi, they are correspondingly, they are one pair. And for linear regression of Y on X, we're assuming like for Yi, like a simple data point from our vector. So Yi is just one value. You can write it as a linear function of X. That's what the linear regression is about. So this is a linear function on X. And we have this EI, which is known as a random error term for YI. And this is important because it gives us some room, like some variation in Y due to some random chance. So essentially it gives the wiggle room around the equation. So this equation is actually a line. You will see that like here. So this regression line, this is this straight line, is the beta 0 plus beta 1 times x. So, and the error, so this EI, well, I put it epsilon I here. I should change this to epsilon I. But for now, just this EI is the error term, and we sometimes use this epsilon I to denote the error term. And this epsilon I is normally distributed. So it's a random variable with a normal distribution, and its mean is 0, and the variance of it is sigma squared. So this is the error term. So this is your line, the beta 0 plus beta 1 times x. And this is the EI, like epsilon I, the distance between this. So this would correspond to y1, let's see, right? This height of this point is y1. So this y1 would equal to beta 0 plus beta 1 times x1 plus this epsilon 1. So this is what this equation is telling you. Is this linear line, the height from that straight line, plus the you will know this is the residual. In later slides we'll define it. But for now, you think this is the error. This is a random quantity, so it will change. Like from this point, it's like this much, but for this point, it's this much. So for this one would be larger, this one is smaller. So that's a random quantity, and we know it's normally distributed, or at least we're assuming it's normally distributed with mean 0 and variance sigma squared. So this is about the error term. And so this error term will give us expected distribution of the points around the regression line. So if we like centered, so this is the expectation of this line, it will be like centered right here, beta 0 plus beta 1 x, and this error term will give us like a distribution around like this point for this single x1, and for each single point you would have like a randomness around this mean, because our error term have mean 0. So like the mean of this y, expectation of this y would be this beta 0 plus beta 1 times x, and the error term would not add up to the mean of expected y, the expected y. And for this bell curve, we know the variance of it is sigma squared. So standard deviation being sigma. So this is the relationship of that error. What this error gives us the randomness around this straight line. Okay, and so this is the structure for linear regression. So we are trying to find this line so that we get a relationship of y on x, between y and x. And how do we estimate the beta 0 and beta 1? Like for this straight line, beta 0 is the intercept of this line, and beta 1 is the slope for this line. How do we do the estimation? So next we'll talk about the parameter estimation in linear regression. And okay, for now we assume from here we know that x and y, they are linearly related. Now you actually will check this assumption in the applied regression class. Well, in this chapter, we'll just assume we know they are linearly related. So we will use beta 0 plus beta 1 times x to model their relationship. Or the true value for beta 0 and beta 1 is, it will be unknown because it's actually like the underlying truth about the whole population. But the data that we collected, like the X and Y, either through experiment or through observational study, we collected some data, like those X1, X2, I mean, X1, Y1, up to Xn, Yn. We collect that data. So we use that data to estimate that line. But that line is actually for the population level value. That's what we're estimating, use the data we have. So, well, we estimate those values, beta 0 and beta 1, by finding the equation of the line that best fit our data. So that means we will choose the intercept and slope so that the line would be as close as possible to our data. So this is saying finding B0 and B1 as the estimates of beta 0 and beta 1, so that this yi hat, so this is our estimated yi, would be B0 plus B1 times xi. This estimate value would be as close as to our yi as possible. So yi is our data, right? We want the, basically you can see this, the predicted value to be as close to our observed value in terms when we are estimating B0 and B1. Well, yi hat is the fitted value. Yeah, fitted value is a more precise way to see this y hat. And the value of the line, yeah, so this yi hat is the value of the line of best fit at xi. So basically we need to find B0 and B1 to make that line as close as possible to our data. So, well, from this plot, well, you might be able to tell what we are doing here. Like we have those data points, like those blue dots here, and we have like the distance of this point from the regression line. So this blue line is the best fit regression line, B0 plus B1 times X. And we the purpose here, well, before that, let's define this residual, like we call this this difference or this distance, the difference between the actual value of y or yi and the predicted value of yi, or the fitted value of yi would be yi hat. So this would be, if this is our y1, x1, y1 data point, so this would be our y1 hat, like right on this line. And the difference of this yi and this y hat, y1 and y1 hat, will be the residual, like e1 hat. So the residual is like the difference between the actual value yi and the predicted value yi hat. So it's the height of the point minus the height of the line. So it can be positive or negative, right? Because we know that this EI, theoretically, it's following a normal distribution. It can be positive and negative, but the mean of it should be 0. And its standard deviation should be sigma. But this is from the data and the regression line. This is how you get the residual. And I introduced this residual because we will need that to estimate B0 and B1. So when we add up the value for the residuals, that's how close our prediction are to the actual value. And we want to minimize like the sum up of those actually squared residuals, and that's called least squares. And this is the way to calculate the estimate for our slope and intercept. And this is called method of least square. Well, put all the equations here. Well, in this least square estimation, B0 and B1, they are chosen to minimize the sum of squared error. So sum of squared error is the sum of squared residuals, or it also called residual sum of squares. So we try to minimize this to find the best value for beta 0 and beta 1. And this residual sum of squares or sum of squared error, we normally just call it SSE, sum of squared errors. And yeah, this is the name, or if you call it residual sum of squares, call it RSS, but they are the same thing. Which is the sum of the squared residuals. So you might ask, why square it? Actually, we do not want to up and down deviations canceling each other out. You know, like EI hat can be negative or positive, but if we just sum them up together, some of them will just cancel. But when we take the square of them, well, we're just trying to minimize the distance. Like we're adding up all the distance, squared distance, they will never cancel out each other. Yeah, we want far or large deviations to be penalized. Well, the larger the distance, well, the worse. So we try to find the B0 and B1 so that this sum of square be as small as possible. Let's see, how do we do the calculation? Well, to find the minimum with respect to B0 and B1, we take the derivative of this sum of square error. So take the partial derivative with respect to B0 and B1, we will get this equation. Oops, sorry. We'll get this equation, and this equation is called normal equations. Well, we rearrange and we get this, and with these two equations, we can actually solve for B0 and B1. So with these two equations, we solve for these two unknown value, B0 and B1. And well, they are called normal equations. Actually, there's nothing to do with this normal distribution. This normal is a term in geometry that means to be perpendicular. The least squares residuals are normal, are perpendicular to the space spanned by x. So that's how it gets the name, normal equations. But anyway, this is how you get your estimate. You get this SSE from, whoops, yeah, we have SSE or RSS. Like this, we take the derivative, partial derivative, and set them to 0 and solve for the equation and solve for
making all the session. I will recommend just mail me anytime. I will try to respond as soon as possible.
Okay, I will, because we have an exam on Monday, and to be honest, I'm not comfortable yet.
Let's see. I muted whoever forgot to mute their mic. Well, let's see. Okay, so this is the normal equations, and this is like solve for that normal equations. We will get the estimates. Well, this looks very complicated, right? So beta 0 is this y bar minus beta 1 hat x bar. Well, you know y bar and x bar is the mean of x and y. And beta 1 is like beta 1 hat is like this. Looks quite complex. Well, we write this as SXY. which basically is this something about x times something about y. And this, the denominator, we call it sxx. So we will learn how to do the calculation in R. Well, this sxx and sxy, they're very common terms in statistics. So that's why they got their specific name. And this is like in word what they are. It's a sum of squares of difference between each x and the mean x value. Is this x? Is this mean x value? You take the square of them and sum them up. And SSY is this, and this. Well, and we can actually write it in a easier or cleaner format. Just get it from the book. So this SXX is this, and we will do this calculation in R. Let's just yeah, before we go to R, let's hold on about the calculation a bit late, to a bit late. And we get this, well, estimates of beta 0 hat and beta 1 hat. And we plug it in, and that's how we get our regression line. Right, this is the whole purpose. And the residuals, they are like this. EI is YI minus YI hat. This is our residuals. And these residuals are the realized value. I should put a hat here, because this is the from our estimation. So these residuals are the realizations for the random error E or epsilon we call. So we said that epsilon or the E is following a normal distribution with mean 0 and variance sigma squared. So yeah, this is, well, let's finish this part before yeah, let's finish this part before we go to R. Yep, we got our residuals, and okay, the variance of E sigma squared, the variance of E, the variance of our error term is this sigma squared, and we call the variance of our regression model is the variance of these residual terms. So is that sigma squared. And this larger variance means larger deviations from the regression line. So to illustrate them, from these two plots, like this one, clearly we have a smaller variance for the regression model, because all these points are really close. The deviations are really small, so they're close to the line. So the variance is small. And for this plot, the variance is relatively large, because those points, well, by the way, the unit, the scale for these two things, we're assuming they're the same, so that we can talk about how close they are or how far they are. So this one have a larger variance, because those points are further from the regression line. And if we compute the variance, because we know the sigma square, it's a parameter, and we try to estimate from the data we have. And previously we did that by using the sample variance. This is the formula for sample variance, and we will do something similar here. So, but here it's like we use this yi minus the yi hat, and yeah, this is the sum of square error. and we summed up the residuals. We squared it first and summed them up and divided by n-2 here instead of n-1. Well, this is actually degree freedom for the SSE. In this case, n-2, because we actually estimated two parameters here. So we got this n-2. Or when we do the sample variance, we have this n-1 because like this x bar, the mean of those x reduce the 1 degree freedom. So that's how you get n-1. But in this case, we had two parameter estimated. So to estimate this sigma hat square, we also call it S square. We use this n-2 as our denominator. Well, yeah, so this is how we estimate this sigma square by this S square. Yeah, let's go to our, yeah, okay. This is, well, maybe it's better we, because it's an example from your book. See, this is example 12.4. Let's maybe, what do we need? Well, let's take a look. Yeah, just, oh, sorry. Let's take a look here about, yeah, so this is the, well, you see this, I think, yeah, I shared the screen for, well, can you see this page, like showing the example 12.4? Because I remember I shared this my Chrome. Well, anyway, this is describing what the data is using for this example. Like this is about the certain number, which is an indicator for the ignition quality of a fuel used in diesel engine. So determine this number is expensive and time consuming. So in this article, it has this data set, and this X is this, okay, X is this value, oops, well. And this Y is this certain number of a sample that they have. So this is the background, like there's some data taken about the chemicals here. Well, let's just take the data and do our calculations. Well, if you really want to know like the background, you can read this, and this is from your ebook on level 9. Well, let's take the value, take the data here to R. So we have a vector of X. So so X is this whole row, whole vector, and Y is this row vector. Okay. And in your homework, you will do something similar, and you take the data from your question statement, define a vector for X, define a vector for Y. Yeah, don't mess up like on the pairs. And let's compute the estimate for beta 0. Oh, sorry, I think I meant to do this from here. That's the raw code. I want to show you this. Yeah. This is the output from that code. So we have this X vector, Y vector, and this is how you code up in R. Part 1, we want to compute the estimate of beta 0, beta 1, and the sigma square. Right. And we know the formula for them already from the slides, though you might not remember at this moment. So I put it here. So beta 1 hat, beta 0 hat, and this S square as the estimate for the sigma square. So, and the formula for this sum of square error is like this. So basically, we will need this SXX, SYY, which is here, and SXY, which needed here and here. So we need to calculate these three things in order to get this estimates. Okay, now you compute, well, you can do this by hand, but I would assume it will be slow. Anyway, let's do it in R. So, well, N we would need, so that's just the length of your data, because we will need this N in this formula. Let's do this sum X, which is this, whoops, well, never mind. So this is the summation of X values. It's actually this thing. And you're basically summing up all the X values in this vector. This is sum X, and this sum Y, which is you are summing up all the Y values in the Y vector. And this is sum S square. So you first take the square of X. So this thing will take the square of each individual elements in your X. So basically this, you first take the square of everything in your X and you sum them up. So this is the sum X square, basically is this thing. Okay, and this sum XY, and it's this summation of X times Y. What is this? And this is corresponding to this thing, right? This sum Y squared. So we basically have those like elements needed to calculate this SXX, SYY, SXY. Now we use these elements to do the calculation. So basically you plug in sum of X squared minus this sum of X, then pay attention here, or just, I go this very slowly because some of you may not know R very well. Like you might wonder why it's like this. So this sum of X, this is this thing. You first take the sum of X, and this whole thing, you take the square of it. So you first do this and you take the square of it and divide by N. Well, similarly for SYY, and for this one, it's straightforward, right? And we use that formula. We listed here. We calculate this beta 1 hat and beta 0 hat, which is the mean of Y, this Y bar, minus this beta 1 hat times mean of X, which is the X bar. And to calculate this SSE, remember we need this SSE, sum of square error, when we do this estimate for sigma square. So SSE is this SYY minus, I'm just plugging everything here. And eventually you get the S square. So this is how you get everything using R code. And once we get to beta 0, beta 1, we can actually do predictions. Well, do predictions means you just plug this in when you are given a new value for X. So if we want to make a prediction for the value of Y when X equal to 100, X equal to 100 is given to you, you want to do prediction of Y, that's our Y hat. So plug this in, this, and the x value. Well, I made a function here that, well, this function is nothing but you give the new value of x, it will just give you back the y hat, because you put this beta 0 hat and beta 1 hat inside, and once you give this new x value, it will return the y hat. So this is how you use it. Well, if x equal to 120. Well, you can always just simply plug it in, like everything x, beta 1 hat, beta 0 hat, you get your y hat. Well, what if we want to do a plot with the data and the regression line? So this is how you do it. When you do the scatter plot, so you have, remember you have a vector of x, you have a vector of y, and this is just telling you like the size. Oh no, this is the, oh yeah, this is the like the shape. Yeah, I think this is shape. Well, sometimes let me just run it here. It will be one, and if I want to do the plot, so this is how you get the plot. Let me just change it. Yeah, that's the shape of your data points. So I change it to 15, it becomes like this black square. 16, so it's a black dot. And how do you get, let me get back to this page. Okay, how do you add the regression line to it? So you just use this AB line. So you first do this plot always, and this is the function to add this line to this plot. And when you add this line, you have to specify what is the intercept and what is the slope. So A is for the intercept and B is for the slope. So basically this line is A plus B times X. So this is how you put your estimation, your estimated slope and intercept, and you give the line type. So it used a dashed line here, where you can always use, well, if you change the number, you will change the type of your line. So yeah, this is the basics. Like you make the plot and you add your regression line to it. And how do you do the prediction? With your estimated slope and intercept. Okay, so this is what this 12.4 telling you, like all the calculations and plotting techniques. Let's get back to our slides where it goes. Oh, it's here. Okay. Yeah, we get how to do the estimation, how to do prediction and plots. And now, how do we assess whether the model is a good model or not? Well, we will use something called R-square to quantify, sort of quantify if the model is good enough or not. Well, we will use a couple things to define the R-square. So here they are. We will need to learn what is total sum of square, like SST, which is the total variability of your data. So it's defined as a summation of this yi minus the mean. So this is sort of the variation for each data point from its mean value, and we take the square of it and sum them up. This is the total sum of square. And again, the error sum of square, or sum of squared error, SSE, is like this yi minus the estimated, like the fitted value yi hat. Similarly, take the square and sum them up. That's sum of squared error. And whoops, sorry, this is SSR, not RSS. Well, this is SSE, and another definition is called sum of squared regression. So SSR, the variability that the model does explain. So this SSR is the variability that your model explains. So this is your fitted value, yi hat, minus the mean of your data, take the square of them, and sum them up. This is the sum of squared regression. It's called sum of squared regression because that's the variability the regression model explained. Well, we got SST, SSE, and SSR. Well, there is a relationship between them. So SST is the sum of SSE plus SSR. So SSE is from our error, so that's the unexplained part, unexplained by your regression model. And this SSR is the explained part by your model out of this total total variability, or like SST, total sum of square of total. Anyway, well, to understand like how they have this relationship, you can think it as like rewrite this yi minus y bar as this two part. So yi minus y bar. So this horizontal dashed line is your y bar, the mean of all your response variable y, and this is yi. See if you have a data points here. So the height is the yi minus y bar is this yellow arrow, the length of this yellow arrow. So it's this thing. So this yellow arrow is the sum of this thing and this. So basically this two. So this one is corresponding to the SSE because like this is yi minus yi hat. And this is corresponding to the SSR. So that's sort of how they are related in this way. Well, now we can get our definition for our square. It's called the coefficients of determination of this regression line. But I think R square is easier to call. It's defined as SSR divided by SST. And we know SSR sum add SSE would equal to SST. So plug it in, like rewrite this SSR, we get this 1 minus SSE minus SST. Oh, this is really confusing, isn't it? It's just those names, they are just hard to call. They're so similar. And this R squared, like this thing, is the amount of total variability in the data that explained by your model. So this is I think this is the formal definition, or well, this formula telling you how to calculate it. But this R squared, it actually means that the amount, the R squared means the amount of total variability in the data that is explained by your model. Well, it can be hard to determine what value of R squared is an indicator of a good model or a bad model. So it's quite subjective, but in most cases, like R squared being above 0.8, 0.9, it's already a pretty good model. But in some cases, R squared can be lower, like 0.6 something, 0.7 something is already good enough. So it depending on like how messy your data is, like how hard to carry out some experiment. Well, it depends. But in general, R squared being like about 0.8 would be considered as good. But anyway, we know that the higher value of R squared, the more successful your model is at explaining variation in Y, right? It's the amount of total variability that your model explained. So we want higher R squared. The higher the better. Well, anyway, there is another term called adjusted R square, which I think will not ask anywhere in your homework, but it normally just show up in many of the output from R. If you wonder what the adjusted R square is, it's just a different version of R square, which takes into like the degree of freedom or like the number of variables into account. But in simple linear regression, you can just focus on this R square for now. Okay, well, we know this R square. Let's see. Yeah, I think in our lab here, I have the code to show you how do we get R squared. So this is another example from the book. Well, similarly, I took the data X and Y from the table on the book. This is your data. This is how you plot it, Y and X, and we'll just repeat it again how you do the calculations. Well, I'm showing you here how to do this R square, because well, we need some of these elements when we do the R square calculation. Let's see that we would need. So remember the formula for the R square is 1 minus SSE divided by SST, and SST is this sum of Y squared. So SST, let's come back. So it's this Yi minus Y bar, and take the square of it. Oh, well, I think there is a easier formula for this. So that's just this. So the sum, this is sum of Y squared. So sum of Y squared. Yeah, first take the square of Y and then take the sum. And this minus the sum of Y, take the square of it and divide it by n. So this thing is equivalent to this. Okay, so we get this SST by this sum Y squared minus this divided by n. So this is our SST. And SSE we have calculated before, right? We showed it from previous example. And this is the formula, and you need the elements, just plug in. So once we get those, we get R squared. Just plug in SSE and SST, you get R squared. And well, I didn't output. Yeah, I didn't output the R squared value. Well, anyway, this is where you find the formula and the code for R squared calculation. Yeah, I think there will be a homework question asking you to calculate R squared. Well, we finish like assessing the model. Eventually, well, what's the time? Well, anyway, eventually we will get to our confidence interval and hypothesis testing. How are they used in linear regression? This is the final part for the linear regression. Well, so before we can make any hypothesis testing or confidence interval, we would need some assumption about distributions, right? We would have to know like what's our variable, what distribution our variable is following, so that we can do the confidence interval, like we did like normal distribution now, and then we can do confidence interval and hypothesis testing, right? So we have some assumptions in linear regression in order to make the inferences possible. So for now, we will make the following assumptions. So we have this linear correlation. So yi is this beta 0, yi related to x, related to xi, yeah. Yi related to xi in this way, by this linear line. And the errors are independent of each other, and they have a common variance, sigma square. You know, we have like E1, E2, up to En, those many error terms. They are independent to each other, and they have a common variance, sigma square, and they are normally distributed with mean 0. So this is saying this E given X is their IID with a normal distribution with mean 0 and sigma square. Okay, this is the assumptions we made for a linear regression model. Well, we have this normal distribution. That's the most important that we can do the inference. Well, before we get to the mathematics to make this chapter, I think this is probably the most important for linear regression is the interpretation. How do you interpret your slope beta 1? And later, after we learn this, we will talk about the hypothesis test on this slope, so that we can tell whether there is a relationship between x and y. Because like the slope equal to 0 means there's no relationship between x and y, right? And we can also find a confidence interval for the size of that relationship, basically the size of beta 1. And this is the whole inference is doing. Okay, the interpretation for the slope is the true average change in the dependent variable y, response variable y, associated with a 1 unit increase in the independent variable x. So if we increase 1 unit of x, how much our y would change. So that's what it means for this slope value. So if we increase 1 unit of x, we will get beta 1 unit increase. Well, depending on beta 1 is positive or negative, right? If it's positive, we say it's increase. It's negative, we say it will be a decrease in y value. So that's the interpretation of your slope. Yeah, so this is the interpretation. If we increase x by 1, we expect y to change by beta 1. Well, we mentioned if beta 1 equals to 0, that means there's no linear relationship between y and x. Okay, well, we knew that beta 1 hat is calculated in this way. And well, we're always assuming x is known because they are normally chosen before the experiment is performed. So we're assuming x is fixed, but y are random. Those y's, they're random, and we can rewrite this slope estimates as beta 1 hat equal to like this is basically a linear function of y. See, from here, all the x value are considered as known, fixed. So this is essentially a linear function of y. So where ci is a constant, well, it definitely involves those x values just by looking at this formula. So we're talking about this because we want to say this beta 1 hat is a linear function of this independent, normally distributed random variables, y. So that beta 1 hat is also normally distributed. So that way we know the distribution of beta 1 hat, right? Because we know like the error term is normally distributed, and y equal to beta 0 plus beta 1 times x plus the error. And now we know y is a normally distributed random variable. And beta 1 is a function of y. So beta 1 hat is, beta 1 hat is a linear function of y. So beta 1 hat is also normally distributed. Well, this is how we get the distribution for this beta 1. And in order to do confidence interval and hypothesis testing, we need to find the mean of this beta 1 hat. We now know it's independent, normally distributed. What about its mean? So, well, we can do proof of this, the expectation of this beta 1 hat by that formula we showed here is actually beta 1. So that is called an unbiased estimator, if you still remember. I just removed the proof, like why this expectation equal to beta 1. But this is true, just believe me. And the variance of beta 1 hat is like this. So well, there will be a long formulas to derive this. But for now, just believe me, this is the variance of your estimate. And write the full distribution of this beta 1 hat is like this. So it's normally distributed with mean being the true parameter beta 1, and the variance being this sigma squared, the true variance for your error divided by your SXX. Okay, now we get the distribution stuff for our slope, estimation of the slope, beta 1 hat. Well, that gave us the ability to do testing, right? If we, let's just do what do we do for hypothesis testing. Well, first of all, I should have, didn't, but just to let you know, just in case you don't, we are testing whether this beta 1 equal to 0 or not. So the null hypothesis would be, null hypothesis H0 being beta 1 equal to 0, and our alternative hypothesis would be beta 1 not equal to 0. And now we'll do the test statistic. Well, first standardize this beta 1, it would follow a standard normal distribution. So if our sigma is known, we can do this, right? It would be a standard normal, but if sigma is unknown, most likely sigma is unknown, we will do this, we will use the small s. Remember, we did we did calculate this s squared to estimate sigma square. So we will just use this s to replace the sigma. And now we get a t distribution, and the degree of freedom is n-2. Okay. N-2. Again, this 2 is just because of degree of freedom reduced by 2, because we have two value to estimate. Well, anyway, you just remember this standardize the beta 1 with the unknown sigma, we will have this T distribution. Yeah, this is your test statistic. This if it's a known sigma, and this is for unknown sigma. Well, we can also get a confidence interval in this scenario because, as we know, the beta 1 hat got a T distribution or it's a normal distribution depending on sigma, right? Known or unknown sigma. If we do this confidence interval, we can just use the formula that we had, like the estimate of this beta 1 hat plus or minus this T score, like alpha is the significance level, normally being 0.05 and degree of freedom, well, and this times the standard error of this estimates. Remember previously we just used this is your X bar, and this is the standard deviation of your random variable of your X bar. And this is just the same thing. This is just replaced by the estimate of our slope, beta 1 hat. And this is replaced by standard error of your beta 1 hat. And these are all as before. And just to remind you, how do you get the distribution value, this T value? This is how you get it. Well, we will have, is this the last? No. Okay, I was too hard to get to like the R lab, but let's finish this first. Well, here I'm just telling you now we can do the hypothesis testing. Normally, let's do it. The hypothesis testing, we are test about this beta 1, and this beta 1 0 is actually 0 in most cases. So, well, let's just use beta 1 0 for now, just in case it goes to other values. Well, this is how you get your test statistic. Just repeating what I said. Yeah. So this is a test statistic, and the p-value will we will do the calculation in R. Well, and this is the output from R. Well, I'm just telling you this. Once you get the output, we will do that later. But once we get this output, we know the t-value, which is actually our test statistic. It will just spill out to you. That's, yeah, it will just give to you. And this p-value, you just get it from here. So, well, from the output, this is the estimates for the intercept and the estimates for the slope. The slope corresponding to this x, because it's the slope for this x. So, and the t-value is, so basically these are beta 0 hat, beta 1 hat, and standard error of beta 1 hat, standard error of beta 0 hat. Well, for now, we only focus on this, like on this line for the slope estimates. And this p-value is doing the test that we are doing at this moment. Beta 0, I mean, the null hypothesis being beta 1 equal to 0, and alternative is beta 1 not equal to 0. And you can tell, well, in this output, the p-value is really small. So it's definitely less than 0.05. So in that case, we will reject the null hypothesis. That means our beta 1, there reject our null hypothesis means there is a relationship between x and y, right, in this case. Oh, yeah, did I make this wrong? Well, this is our t-value, and this is the standard error for this estimate. and this is your p-value. And this p-value is testing this hypothesis. Okay. Now let's get to our, oops, no. Yeah, let's get to, yeah. So let's just following up of this data, which is from the example 12.11 in the textbook. We calculated the R square here, and we plotted the data and added the regression line here. Now we do a confidence interval for the slope parameter. Do a confidence interval for our beta 1, for our beta 1 hat. So as well, this is again the elements to eventually get our test statistic. And yeah, sorry, yeah, my brain is stopped working. Not test statistic. We're doing confidence interval for the slope parameter. So this S is oh yeah, this S is the estimates for sigma, right? Sigma is unknown in this case. We're estimating this sigma from here. Remember the formula to estimating sigma squared by S squared. So this S, we will need it in our test statistic. Okay, no, not test statistic. In this, oh yeah, this is something I'm preparing for the test statistic. Oh, this is how I manually calculate the standard error for your beta 1. So standard error for your beta 1, remember, is this, you are taking, let's get back here. Is this thing. Is this S divided by the square root of SXX. So this is how you calculate the standard, standard error of this beta 1 hat. Okay. Yeah, so this is how you get, remember this is squared, so you take the square root, you get S. Actually, I should just put S here because I have already calculated. So this is S divided by the square root of SXX. Okay, this is the standard error of your beta 1 hat. And our significance level is 0.05 and degree of freedom n-2. Now we get our, yes, it is the test statistics we are doing here. Well, why I said it's confidence interval. Because, oh yeah, I did both the test. Like this is the test statistic, like the t-value. So we just put 1 minus alpha over 2, and we supply our degree of freedom. Oh yeah, I think, yeah, I made this. I take that back. We're doing confidence interval. Sorry, we're doing confidence interval here. This t-value we are calculating is this t-value. Is this t-value, okay? This is the t-value we are calculating. And because we will need the standard error of this beta 1 hat, and also the estimates, okay? So standard error of beta 1 hat, this is one element needed, this is the t-value needed for the confidence interval. So this is the upper bound for our confidence interval, this is a lower bound. Yeah. Okay, this is a confidence interval. Well, hypothesis testing. Oh yeah, I think the hypothesis testing I did in the last example. Okay, last example here, example 12.12. So this is basically, well, again, if you want to get more like the background of this example, you should go to your ebook and find this example. We'll just skip that for now and just extract our x value and y value and do our calculation. Okay. Yeah, for this one, we are doing our hypothesis testing. Okay. Well, this are repeating what we did for calculating this like SSE, like estimate for sigma square to calculate our S square. And eventually we get the square root of beta 1, the square error of the beta 1 hat. And that's something needed when we do the hypothesis testing. So, well, when we do this hypothesis testing, we would need the test statistic. Well, let me see where I get to the, oh yeah, this is your test statistic. Oh yes, here, this is your test statistic. Okay, this just refer back to, yeah, to this, like beta 1 hat minus 0. Remember, this is 0, so it just comes back to like beta 1 hat divided by the square root of beta 1 hat. Okay, this is how you, why it's beta 1 hat divided by this, because we just minus 0 here, it's just gone. So this is how you get the beta 1, the test statistic. And for two-sided test, remember our alternative hypothesis is beta 1 not equal to 0. So in that case, when you calculate the p-value by hand, you will do this, like you will do this 2 times the one tail area. So this 2 times the area under this t curve to the right of your test statistic. And in R, this is how you do the calculation. So this is basically repeating what we did for the hypothesis testing chapter, but you just need to calculate the standard error for a beta 1 hat, and definitely you will need this beta 1 hat. That's almost always your first step to do the estimation. Well, this is how you do it manually in R to calculate the p-value. Well, I show you in the slides, you can actually do it fairly quick by doing this linear model. Like once you have your X value and your Y value, you do this linear model. Yeah, you do this linear model and do a summary of it. It will just pop out like this table for you, and it will give you the R square for this model, like the R square. This is the R square that we actually calculated previously by hand. By step by step in R. But this is how this linear model gave to you. And well, look at this p-value. It would agree with the step-by-step calculated p-value, right? And you can actually get the p-value from here, and the estimates it give to you, and well, you can calculate from like step by step, like do all this little thing and calculate, use our formula to do the calculation. You can definitely verify if you calculated right or not. By this, you just do this model this is your function Lm. Remember, it's always y tilde x. Do not switch the order of these two. And this is how you get this output of your model. Okay, and this is how you get your beta hat. Extract the beta hat value from this model. Okay. Well, maybe it's better I run this for you. Oh, it's really dark. Okay. Let me do this, run this X and Y, and do this model, this linear model. This is the output. And actually you can do this model $ coefficients. Let's take a look at what it is. So this model $ coefficients is giving you the estimates for the intercept and the slope. Well, the first element would give you the beta 0 hat, and the second would be your beta 1 hat. Okay. And this is how you do the plot and add the regression line to it. Okay, there it is. Yeah, here they are. Okay, so yeah, I think for your homework, you can choose freely like which one you want to. Well, definitely this step-by-step calculation is complicated. But I think for the book, well, actually you actually do this in your applied regression class. But in this class, you are supposed to do like this manual calculation to get your estimates. But well, you're free to choose whichever one to use, or you just do your verification on your own if you are just curious. Okay. I'm just giving you all the resources to do your homework. Well, I guess that's it for today for the linear regression. Well, I was planning to have two lectures for linear regression chapter, but it looks like we can actually do it in one lecture. So in this way, I can kind of put the following chapters for this class a bit earlier. That way you have no homework in your Thanksgiving holiday. So I think this would be better. Yeah, I don't want to really drag in the class time. If we can like finish in one lecture, I don't want to do it separate in two lectures. Well, yeah, I will post this lab, this file, this HTML file on Blackboard, and the slides is already up there. Yeah, I believe. If there's no more questions, yeah, do you have more questions for me? Okay. If there's no more questions, I think I will first stop recording. Yes, we will end it here. Stop recording.